Welcome to an exciting presentation where you get to listen to a potato with a creepy voice rant about math and algorithms. Today, we're going to look at recursion and see how efficient it is. We actually see recursion a lot in nature. A nautilus shell has a Fibonacci spiral. We can see repeating geometry in honeycomb. Certain types of broccoli are composed of fractals, and even God himself is recursive by nature. One of the best examples can be seen in the branches of trees. So if recursion is so efficient in nature, then is it equally as efficient as an algorithm? Maybe it depends on the nature of the algorithm. So we're going to use a binary search tree to test whether or not recursion can beat iteration. After all, it's only fair to have iteration fight recursion in recursion's home territory. So here's the idea. We're going to write iterative functions to traverse a binary search tree and then compare the times to their recursive counterparts. We'll be writing in-order, pre-order, and post-order traversals. Now we've all seen the pseudocode for these in recursion. Pretty soon you'll see the horror of what it looks like written iteratively. To spice things up a bit, we'll be using different data structures for our iterative functions, and we're going to see which method comes out on top. So to make our tree, we'll be using a node class that holds pointers to our left and right child nodes. Next, we'll make a tree class that utilizes those nodes. We'll need a function to insert them into the tree, so let's take a look at the code for that. The algorithm's pretty basic. We have a few pointers to help us traverse the tree, and we're creating a new node based on the data we took in. Without explaining it line by line, it should be pretty apparent that we're just checking to see if each node has a left or right child, and then comparing the data values. In the end, our node is properly placed. Our first traversal function is post order, which is going to utilize a bool to help us keep track of which nodes we visited. There's also a pretty nasty flaw in this that hopefully everyone can see. Just remember, we're going to be making trees with over 1,000,000 nodes. If each node has a bool, then that's 1,000,000 bools to process. Anyway, since we're doing post-order traversal, then we know our priority is left, right, and then root. So we're essentially moving a temporary pointer through the tree and checking if a node exists and whether or not we've been there before. For our pre-order function, we're going to utilize a stack. Now the downside is that our stack has to be as big as our tree, since it's going to have to hold all the nodes. Plus we'll be doing a lot of pushing and popping, so there's still a lot of operations going on. In this case, our priority is root, left, and then right. So we'll start by pushing root onto the stack, then looping through the tree, outputting the data, and pushing our left and right child nodes onto the stack. Since the first thing we did was push root onto the stack, and the last thing we did was check to see if we have a left or right child node, then we can simply loop by checking to see if the stack is empty or not. And that brings us to our in-order traversal, which is a nightmare of an algorithm. The previous two sorting methods and even the insertion function didn't pose that much of a challenge. Now I could have used a stack or a queue for in-order, but I wanted to use a different approach for each traversal. So I came upon the unfortunate discovery of Morris traversal. This algorithm was written by Joseph Morris back in 1979, and it's pretty convoluted. It may not look threatening. I mean, hey, it's just a bunch of if statements and a couple of while loops, but here's what it actually does. Essentially, we're restructuring the tree so there are no left children. Eventually, our entire right branch is a perfect in-order traversal from the root to the final right child. Now, here's where this algorithm goes from 0 to retarded in an instant. Through arcane and eldritch wizardry, this else statement, it actually repairs the tree back to normal. Any further explanation, and I'd end up eating way too much of my time here. So we have our three traversals. Let's take a brief look at what the recursive versions look like. And they're basically 3 lines of code. We do a base check, and then we either output data or traverse the tree. The question is, will our call stack run out of memory when we sort a tree with 1,000,000 nodes? So let's start with just a tree of 10 nodes, just to make sure everything works properly. So the output shows that each sort function is working, so that's good. So far there's no real difference between iteration and recursion, so let's up it to 100 nodes. And recursion is lagging behind by a fraction of a second. How about we just move on to 1,000 nodes? And recursion takes the lead again, but not by much. So let's do a quick check to make sure our times are doubling along with our data sets. So now we have 2,000 nodes and our processing times do appear to be doubling. Let's just go ahead and take it up to 10,000 nodes. And recursion is still more efficient, but our bool function is strangely coming close to beating recursion. So once again, let's double the data and see if the times double. And our times are indeed still doubling. Well, this is kind of boring, so let's try a few numbers in the 6-digit range, starting with 100,000. The biggest thing to notice here is that processing 100,000 bools is apparently more efficient than using a stack with 100,000 nodes inside. Maybe it's all the pushing and popping, or maybe we just haven't hit a large enough number to cause any slowdown. As usual, we're going to double the number and see if our times are also doubling. And the times are indeed doubling, and our stack function is performing horribly. So the time has finally come for a 1 million node tree.
One eternity later.
Okay, well that took like an hour for everything to process, and I'm running a Core i7 with 32 gigs of RAM. So first thing to notice is that our program finally got angry at having to process a million bools. There is roughly a 10-second difference between its recursive counterpart. That means our iterative solution is running about 33% slower. Even our stack function is 3 seconds behind the recursive version, which is right at 22 seconds. The closest iteration is getting to beating recursion now falls in the hands of Morris traversal, which is actually beating recursion by a fraction of a second. Let's make a 2 million node tree and see what happens. And Morris traversal is lagging behind by about 4 seconds. The stack function is about 15 seconds behind, and I don't even want to talk about the bool function. So I guess we should probably talk about the bool function. That function, if you haven't already noticed, it has a time complexity of O of n squared, but it's only a worst case scenario, and it's not that likely. It's only because in certain situations we may have to move our pointer back to the root node after visiting each node. So right now we're definitely seeing O of n squared runtimes. So how about a 3 million node tree? And 3 hours later it finally processed, and bool is back to doubling its time instead of tripling. So if you haven't already noticed, the recursive functions are increasing the slowest. At this point it may be a lost cause to try and beat recursion. Morris traversal is the closest, but with a 3-second difference, so I don't think it's possible to retake the lead. And I honestly thought iteration would win. I gave it a 98% chance of winning. Now, listen, I might be so far to the right that I make the alt-right look like centrists, but looking at these numbers, I feel like a liberal on election night. Iteration should have won. This experiment was clearly rigged by Russian recursion, and I don't know how to admit defeat, so let's make a 10 million node tree. Okay. Okay. Well, that was fun while it lasted, but unfortunately, recursion finally tore the call stack asunder. So the question is, how did recursion not run out of memory until 10 million nodes? Like, if I ask this Fibonacci function for the 20th element, then it has to make 6,764 calls before returning the answer. You can crash a simple factorial recursion just by tossing in the number 4,500, so why did recursion run out of memory somewhere between 3 and 10 million nodes? And the answer to this lies in the call stack. Each time a function calls itself, it pauses the function and lets the recurse take priority on the stack. Each stack is held in a different location in memory, so it makes sense for most recursive algorithms to run out of memory if the dataset is too large. So the reason why we didn't run out of memory this time is because of the way binary search tree sorting works. In each recurse, we're either checking the left or right child and then moving down the tree. So what does that mean? Well, it means that function calls are going to rapidly be popping on and off the call stack. So memory is going to constantly be allocated and then freed up at a steady rate. But that only works because of the way binary search trees function. This is why binary search trees are recursive in nature, but in this case the call stack is also working in favor of recursion. So now it makes sense that recursive Fibonacci freezes up, since we're not consistently freeing up stack space. So in conclusion, recursion won the battle. We also found out why it won. Since binary search trees are recursive in nature, and our call stack never filled up till we ran out of memory. On a final note, we can also say that many recursive algorithms are pretty simple and easy to understand. So the lesson here is to look at how your algorithm functions. If it has a recursive nature or a pattern of repetition, then it may benefit from being written recursively, but you also have to remember how memory works. So, thanks for watching.